Good evening. Welcome. I'm Gina Vild. I'm the Associate Dean for Communications and External Relations at Harvard Medical School, and I'm delighted to see you here for our second Longwood seminar of 2015. And welcome to all of you who are joining us through live streaming tonight. Last week, we had viewers from 16 countries join us to learn more about the impact of medical innovation and to learn about the new technologies being developed at Harvard Medical School. If last week serves as an example, tonight we are delighted to welcome people from as far away as Australia, Canada, Egypt, Greece, Ireland, Mexico, Morocco, the Netherlands, Saudi Arabia, Romania, Spain, Switzerland, Bahrain, the Ukraine, and beyond. So thank you for joining us. Wherever you are, I invite you to join us on Twitter and share your thoughts about tonight's Mini Med School. Our hashtag is hashtag HMS Mini Med and hashtag allergies. Both of these are listed on the screen behind me, as long as other information we would like you to have. If this is your first year attending the Longwood seminars, I invite you to look at the archives of all the past seminars from the past 3 years, which you will find on our website. And in the next month, you will find this year's Mini Med School seminars on the website as well. Tonight's seminar, focused on understanding food allergies, is the second of the 4 seminars. And I hope you're going to join us for the next one on April 14th, called Music as Medicine, The Impact of Healing Harmonies, which will be a very special evening, and I'm very sorry I'm going to miss it. The 4th and final seminar, Diseases Gone Global, What Causes Epidemics, will be held on April 28th. If you have questions about how to earn a certificate of completion or professional development points, please ask a member of our team in the lobby on your way out. And of course, thank you for turning off all electronic devices. George Bernard Shaw wrote, "There is no love sincerer than the love of food." Is that not true? But what happens when the food you love doesn't love you back? What's going on when peanut butter makes your throat tight? What does it mean when bread makes you feel ill? Or when milk upsets your stomach? It seems that adverse reactions to food are becoming more common. In fact, how many people here either have a food allergy or know someone who does? Almost all of us. In our society, it's becoming more and more common to have peanut-free policies in schools, in daycares, and on airplanes. And it's common to see grocery store shelves filled with gluten-free, dairy-free, and soy-free products. But what exactly is a food allergy? What's happening inside of our bodies that makes us feel unwell, that gives us hives, or makes our throats tingle? Are these symptoms of an allergy, or could they be something else? Tonight's experts will explain exactly what a food allergy is, and will share with us the latest science on the biology, pathobiology, and food allergy. They will explain the role of the microbiome in food allergies and the causes of allergies and other adverse reactions to food. And they'll share with you some leading stories as to why food allergies seem to be increasing, not only here in the US, but around the world. I'm delighted tonight to introduce our speakers, exemplary members of the Harvard Medical School faculty who work every day to contribute to the understanding of the biological, genetic, and environmental factors involved in the food allergy and autoimmune responses. Dr. Jessica Savage is a Harvard Medical School assistant professor of medicine at Brigham and Women's Hospital. Dr. Ramnik Xavier is the Kurt J. Isselbacher Professor of Medicine in the field of gastroenterology at Massachusetts General Hospital and HMS. But first you'll hear from Dr. Wayne Scheffler. Dr. Scheffler is an Associate Professor of Pediatrics at Harvard Medical School. He is the director of the Food Allergy Center and the principal investigator of the Center for Immunology and Inflammatory Disease at Massachusetts General Hospital. He is the assistant pediatrician and the chief of pediatric allergy and immunology at Mass General Hospital for Children. And he has developed a highly integrated research and clinical program to better understand the pathogenic mechanisms of food allergy and asthma and to provide the best care for patients. So please welcome our guest tonight.
Thank you, Gina. It's a pleasure to be here. This looks just a little off. Let me see if I can. There we go. So it's a real pleasure to be here and participate in this distinguished lecture series and to join my colleagues from the Harvard community on this topic. I understand last night there was a Harvard Catalyst, which is an NIH-funded effort to make us all better clinical and translational researchers on using improv techniques for doctors to be better speakers. And unfortunately, I did not have the benefit of that last night. So I apologize if I'm not as engaging as I might be, but hopefully the topic will engage you. I'm a cellular immunologist primarily in terms of the research I do. I'm not actually going to talk all that much about any of the science going on in the lab, but instead use the time I have to give a clinical overview of food allergy and sort of to address Gina's comments at the beginning about what is a food allergy and what distinguishes it from other adverse reactions to foods, talk a little bit about how we make the diagnosis. I need to educate you a little bit, if you don't already know, about the differences between immediate kinds of food allergies and delayed types, which Dr. Xavier will talk in more detail about later. Talk a little bit about management now, or what Dr. Savage will define for us better later as is tertiary prevention, and give just a little bit a glimpse of what I think is coming in the future before I then pass it on to these guys for what is probably the most interesting question right now, which is why is it becoming so much more common and what role does the microbiome play? So let's start with the ways in which foods can make us sick. So one of the things that Dr. Savage will talk about in terms of the epidemiology of food allergy that makes it so difficult is that there are a lot of ways that foods make us sick. And so when you ask sort of an audience, maybe even an audience like this where there were a lot of hands went up about food allergies, you tend to get overestimates because in fact there are a number of ways that things that we eat can make us feel ill. Not all of them meet the technical definition of what we regard as a food allergy. So for example, people can have toxic reactions to foods. A good example of this, because it in fact can mimic many of the signs and symptoms of allergic disease, is something called scombroid poisoning. That is most often associated with spoiled fish, and the bacteria that causes it actually produces histamine and histamine-like molecules that have then, upon ingestion of that food, the effects that histamine released by immune cells have and causes flushing and potentially hives and potentially respiratory difficulty, et cetera. This was one story about that in the New York Times I referred to. It's actually very entertaining. Then there are also metabolic activities of some foods that we don't regard as really either toxic or non-toxic. These are in fact, in some ways at least, expected activities of foods, at least in a subset of the population. So a classic example would include the flushing reaction that occurs to some people in response to alcohol. Caffeine withdrawal can cause migraines. Perhaps MSG reactions in large part fall into this category, and perhaps even some of what we call sulfite allergies might fall into this category. But allergies fall into this category of what we call non-toxic reactions. Now, here also, there are a number of non-allergic causes of adverse reactions to foods. One of the most common would be lactose intolerance caused by a deficiency in the enzyme that digests that sugar. And so if you consume large quantities or sufficient quantities of lactose and you lack the enzyme to digest that, you'll get bloating and symptoms that are related to the malabsorption that occurs consequently. There are also psychological reactions that can occur in the context of food ingestions, principally panic attacks. And these, in fact, to some extent may overlap with allergic disease as well. And so then we come to this category of immunologically defined adverse reactions to foods, and it's here really that we're going to focus the talk on today. It's here that we see allergic disease, and these can be both IgE mediated, which I'll define subsequently, or non-IgE mediated, but also in this category would be celiac disease, although we think of that mechanism as distinct, it is immune mediated. And it meets this definition that the NIH put out in 2011, a consensus statement definition of an adverse health effect arising from a specific immune response that occurs reproducibly on exposure to a given food. And this is not only a helpful definition, I'm getting a little ringing there, I don't know if you can adjust that some, but it's useful in clinic day to day. So when I am evaluating a patient who has an adverse reaction to food and I'm trying to figure out whether or not it's an allergic response, there are keys like the reproducibility that I'm looking for in that history to decide whether or not this is likely to be an allergic reaction. Allergic reactions tend to also, because they are immune-mediated, require, generally speaking, small amounts of exposure to trigger a response. So that's what the immune system has evolved to do very well, is to respond to a small amount of foreign antigen. And the IgE-mediated arm in particular does that with exquisite sensitivity and very quickly. So these are features that distinguish food allergies from other adverse reactions to foods. So I started to talk a little bit about the history of how we make that diagnosis. I want to take one step back, and I can't really be a bona fide immunologist without showing at least one cartoon like this that describes some of the players of the immune system and how it is that the immune response becomes an allergic one. So very early on, there are sentinel cells throughout the body that are constantly surveying the environment for foreign antigens and presenting those to other immune cells, principally CD4 positive T cells. You've heard about CD4 positive T cells because they're depleted in HIV. These are really the orchestrators of the immune system. And under the right conditions and with, to some extent, the right genetic background and perhaps from other influences that we'll hear about later, this response can be skewed to what we call a Th2 or allergy skewed response. It's these cells then that consequently drive much of the pathology that we associate with allergic disease in general, whether it's an environmental allergen causing hay fever or asthma, or in the context of tonight, a food allergen that causes the signs and symptoms of allergic disease. And this is true, this early part of this immune response in both IgE-mediated and non-IgE-mediated food allergy. What separates the two is, in some cases, the T cells, in addition to doing things like recruiting inflammatory cells, instructs antibody-producing cells that we call B cells to switch their production of antibody to this class that we call IgE for historical reasons. And it's that IgE antibody that then arms effector cells of the immune system, like mast cells that reside in the tissues throughout our body. And these are the ones that, upon the second exposure of allergen, degranulate is the term, the jargon term, but basically they release the contents of these granules. They're already made, they're primed, they're ready to go, and prominent among those contents is histamine, as well as other things. And so that's why that response can be so quick. It's because the immune system has previously seen the antigen, it's become sensitized, and now produces, in some people, IgE that arms those cells and hence can produce very rapid responses. And so it's largely IgE that we're measuring. However, there is an imperfect relationship between the presence of IgE, a state, an immune state that we call sensitization, and diseases associated with it, including food allergy. So as I already mentioned, there are forms of food allergy that are non-IgE mediated. There's the immediate subset that is IgE mediated. Some of those individuals may also have a disease such as atopic dermatitis or eosinophilic esophagitis, as we'll hear more about from Dr. Xavier. We have to keep sort of this incomplete overlap in mind when we're evaluating the patient. So when do we test for IgE? Well, the obvious time we test for IgE is when the history is consistent with immediate signs and symptoms of a potential reaction. So most of what I do, any of you could do, patient comes into the clinic and says, my 12-month-old had peanut butter on a cracker for the first time and immediately had runny nose and hives and vomited, and hopefully no worse than that. And they tell me, I think that, my child has a peanut allergy. And, then I say, yes, you're right. And they don't really need me to do that, do they? So often it's very obvious that we're testing IgE to really just confirm a diagnosis where the history already gives us a very, what we might call, high pretest probability. Sometimes, though, it's not so obvious. In some forms of food allergy, and I apologize for the acronyms I haven't defined here, but this is eosinophilic esophagitis, this is eosinophilic proctitis, this is food protein-induced enterocolitis. There may be other reasons that a clinician will measure IgE, in part because they may be developing an overall picture of the likelihood of a diagnosis that's associated with the presence of IgE, in part because they may be manipulating the diet and there may be some risk on a future exposure to an allergen being associated with an immediate reaction, or in part because it has prognostic value in predicting the future course, the natural history of a patient's presentation of food allergy. We measure this in one of a couple of ways. Skin testing, it's a very old test. It involves applying an extract that contains a diluted solution of allergen to the skin and a very small needle that breaks just the superficial layer of the skin, and it elicits a wheal and flare. This is the effect of mast cells in the skin releasing their preformed contents because they've already been sensitized. They already have IgE on them, and we're just demonstrating its presence in this functional test. The other way that we look at it is on some sort of solid phase assay where the allergen in question is bound to this surface, and we take serum, the serum component of blood, and allow antibodies, including potentially IgE antibodies, to bind to those antigens and then detect them in this assay. And so those are the two principal ways that we measure it. And there is a relationship between how high that concentration of IgE is, or in fact how large the skin test is, and its predictive value. So the higher the IgE is, or the larger the skin test is, the greater the likelihood that that person does have immediate food allergy or IgE-mediated food allergy. But there's also a lot of discrepancy between the presence of sensitization and clinical food allergy, and I'll just move right from left. There's also things evolving over time, so this is a moving target. Some people have early sensitization, but never are clinically allergic. They, in fact, tolerate the food despite the presence of detectable IgE. Some people have sensitization that then resolves, and of course, they're clinically tolerant. They have no IgE at all. Some individuals have early sensitization with clinical food allergy but outgrow it, and others have persistent allergy. And we'll hear a little bit more from Dr. Savage about the prevalence of this problem in the population, but it varies. The prevalence is different by age because of this phenomenon of some people outgrowing it, and this is true for some allergens more than others, as Dr. Savage will tell us more about. So because there is this relationship, we don't have really, a binary test that is simply positive or negative. We always have to evaluate the pretest probability from the history and then use the IgE testing to help us with the diagnosis. So I've painted a scenario here where someone comes in and you're just really not sure. The history is sort of a 50-50. If they have a very high IgE, that has a strong positive likelihood ratio, and it means that after doing the test, if it's strongly positive, they very likely do have food allergy. On the other hand, if that test is negative, it has a very strong negative likelihood ratio, and so the person that comes in with a possible history of immediate food allergy is ruled out by a test like this. And that's really where it's most helpful, but as you might have picked up as I moved through there pretty quickly, maybe you didn't, there's a very large gray area. And so we still, in 2015, resort to this very sophisticated test of feeding children allergen and seeing if they react. And this is called an oral food challenge. We do a lot of these. In fact, we've done almost 1,000 of them here just since I came to Boston, and many thousands that have been reported in the literature. And this is done safely by giving it in a graded fashion with monitoring of vitals and the availability of medications to treat people should they react. So that's how we make the diagnosis. Let's talk about management. It remains the case that management today consists of avoidance of the allergen and an emergency action plan that includes the use of and indications for autoinjectable epinephrine. So this is still 2015. This is our management. This is our tertiary prevention. So action plans defined by the symptoms of presentation, what the response should be. In general, if there's any airway involvement or multiple organ systems involvement, epinephrine is really the indicated medicine. For very mild reactions, it may be appropriate to use antihistamine and observe. What I think is probably most lacking in management, and I want to try to address in a public forum a conversation that I usually restrict to having just one-on-one with patients because it can be a little bit tricky to talk about, but we don't have a very good way of assessing some of these things. When I see patients, and especially patients, the parents of patients, one of the most pressing questions they have is, how allergic is my son or daughter? And what they mean by that, of course, is how much risk are they exposed to? How sensitive are they to a low exposure? How serious a reaction may they have? And they need this information, obviously, in order to make informed and appropriate decisions about how they're going to balance, essentially, the lifestyle of their child with avoidances versus normal activities of childhood. And there's also a public health implication. So one way that we've tried to address this is actually with a study where we brought in about 400 kids with peanut allergy and simply gave them a low dose of peanut allergen under a controlled setting. And this was about 1.5 milligrams of protein, which, by the way, is about 10 times more than what you'd expect from a candy bar that says may contain traces of peanut on it. And in fact, about 5% of children had a visible reaction. All those reactions were mild and treated with antihistamine or just observation. This is about what that looks like in peanut butter equivalents. It's a little bit under 2 milligrams. This is sort of the range that is more often associated with reactions that can be more significant. It's once you start getting up into the tens or hundreds of milligrams of ingestion that you're at greater risk for strong reactions. Contact exposures, as has been shown actually in controlled studies of putting peanut on the skin of people with allergy, is not a very easy route to elicit severe reactions. It's really first and foremost ingestion that we have to worry about, and it's ingestion of relatively large amounts of peanut protein. This is what that roughly 50 to 100 milligrams of peanut butter looks like, for example, on a button. And so you'd have to imagine, most likely that kind of really being ingested to create a severe reaction. But contact reactions can be pretty impressive and scary looking, no doubt, and certainly not trivial by any means. Finally, in thinking about risk, I think we have to help our patients contextualize that. And so we need to think about, what is the risk of that pediatric patient with food allergy, as these authors did. They looked at a total of about 250 of food allergy-related fatalities. It represented a couple 100 million allergic person years, and put that risk in the context of other things such as accidental death, et cetera. And what you can see is that when thinking about how you're going to make decisions about lifestyle, et cetera, it's important to put that in the whole context of other things. There are a few things that we are aware of in terms of risk factors. Adolescents, that's mostly behavior related, making poor decisions if they do have a reaction or not speaking up about their allergy. Poorly controlled asthma, this is another thing that we can definitely control to reduce the risk. Some food allergies are more associated with severe reactions than others, and that's something that we have a good sense of. What about the future? So the concept of allergen immunotherapy is certainly out there. This is just a Google image search on the term oral immunotherapy, which is actually not a term that is restricted to food allergies, but basically everything that pops up is food allergies. I'm sure many people in the audience are familiar with this concept of introducing small and increasing amounts to the diet with the goal of inducing protection. In fact, this is still research. Studies have shown that while desensitization, in other words, as long as you're taking a daily dose, you have some protection against subsequent exposures, is achievable in the majority of subjects, it comes at the expense of a fairly high rate of adverse events, and that protection for most people appears to be lost with time. So we're very interested in what are the mechanisms that really define those individuals who have persistent tolerance from those individuals who have just a transient benefit, and try to better understand that. And what we hope is for the future that we'll move from sort of 19th century equivalent of vaccinology. This is an image of Edward Jenner administering smallpox vaccination initially with viral extracts. Where that field has moved in the subsequent couple hundred years has been to defined vaccines with defined adjuvants that drive the immune response the way that we want. This is, I think, really the next step and future for food allergy research as well. And I will back out of here. And I have the pleasure now of introducing Dr. Savage, who will. So this is where it gets, I hope, even more interesting, because the next two speakers are really going to address this question of why is it more frequent. So Jessica is an assistant professor of medicine at Harvard Medical School, an allergist within the Division of Rheumatology, Immunology, and Allergy at the Brigham. She is the director of population studies in allergy, director of the Brigham Food Allergy Center, and a member of the National Institute of Environmental Health Sciences Center at the Harvard School of Public Health. She completed her medical training at Johns Hopkins in Baltimore, where she also completed a master's degree in epidemiology before she joined faculty here at Harvard in 2012. Her primary research interests focus on the environmental and genetic factors that influence the development of food allergy and that may contribute to and underlie the recent rise in allergic disease. She's specifically interested in how environmental antimicrobial chemicals may influence this risk through changes to the human microbiome. And I've known Jessica for some time. She's a fantastic colleague and scientist, and it's my pleasure to invite her. I welcome her.
Thank you, Wayne, and thank you for coming to this talk. And I now have the pleasure of talking to you about the epidemiology of food allergy. So for those of you who are not really familiar with the term, epidemiology is a science that studies the patterns, causes, and effects of health and disease disease conditions in defined populations. And I think before I get started, it's really important to tell you that the epidemiology of food allergy is very challenging to study. There are a couple reasons for this, and one of them is that actually doing a food challenge on everyone is very difficult because this imposes significant risk, and it is very time consuming. So the gold standard for diagnosis of food allergy cannot be done on a population level. Also, we know, as Dr. Schreffler said, that the testing for food allergy by skin testing or blood testing is imperfect, and there are far more people who test positive for food allergy than actually have allergic reactions when they ingest a food. Similarly, if we rely on asking people if they have food allergies, this is also imperfect because more people think they have food allergies than truly have food allergy. And finally, observational studies, which is where we actually look for correlations among environmental factors and patient characteristics, these are really limited in what we can actually learn from them. And then experimental studies are challenging, especially in children, and these are the people who are generally most affected by food allergy. So now I'll tell you what we do know. So we do believe that the prevalence of food allergy is between 4 and 10% of children and between 2 and 3% of adults. And this is generally because children start with food allergy and tend to outgrow it over time, although there are exceptions to this rule. So one interesting thing is that we see a similar prevalence of food allergy in the developed world, and this is really with no to low prevalence in underdeveloped parts of the world. And so this raises the possibility that there are shared risk factors associated with a quote-unquote Western lifestyle. Our best evidence suggests that the prevalence of food allergy is increasing, and this is possibly due to more people becoming affected with food allergy, and also due to people who do have food allergy taking a longer time to outgrow their allergy. So we all know that we have an epidemic of food allergy, and here I'm showing you the results of a meta-analysis of several population-based surveys of self-reported food allergy that I had the pleasure to work on. And this was using studies only from the United States over the last 15 years. We looked at survey data taken every year using similar methods from over 400,000 children in the US. And here we show a steady increase in food allergy prevalence over a recent time period. This overall represents about a 1.2% increase in food allergy prevalence per decade. So as I showed you, food allergy is a disease that affects about 10% of the population or less. So therefore, this 1% increase per decade is a dramatic increase, showing that the prevalence of food allergy has nearly doubled in about the last 20 years. So in addition to showing this remarkable overall increase in food allergy prevalence, we were also able to show marked differences in the rate of food allergy by race and ethnicity. And so here I'm showing you the percent increase in food allergy per decade. It's roughly 1% overall, but this rate is nearly double in African Americans, and it's higher in Hispanics compared to Caucasians. And the reason for this disparity is really not known, but it needs to be investigated. As you know, peanut allergy is the leading cause of anaphylaxis and death due to food allergy, and we're all affected by peanut allergy, even if we're able to enjoy eating peanuts, because there are now peanut-free classrooms, peanut-free schools, and peanut-free airlines. So some estimates suggest that the prevalence of peanut allergy may have actually quadrupled over the last 13 years, perhaps even rising faster than the rate of food allergy in general. So as I alluded to before, there are two reasons that we may be seeing an increase in the prevalence of food allergy. Prevalence refers to the number of people who have food allergy, and this can increase if the number of new cases of food allergy increases, and it can also increase if the people with food allergies are taking longer to outgrow their food allergies. And I'll show you an example of this. So based on papers from the 1980s, it was thought that most food allergy was transient or outgrown before a child would enter school around the age of 5. And so we actually wondered about this because we were seeing children in our clinic with food allergy who were basically not outgrowing their allergies and developing into food allergic adults. So we decided to study this, and we observed that children here in this example with egg allergy were outgrowing their allergies around an average age of 6 to 12 years. Some were earlier and some were later, but that was the general trend. And this is very different from the dogma that food allergy is outgrown before a child will go to school or enter kindergarten. So why is food allergy increasing? Well, we don't know right now. We're working on it, and I'm going to tell you two of the main ideas that in some of these you may have already heard about. So when we think about causes of disease, we think broadly in categories of genetic and environmental causes. And for food allergy, we do in general feel that there is something in the environment that has changed that is contributing to the rise that we're seeing, because changes in genetics would take far too long to explain this rapid rise in food allergy. The two topics that I'm going to share with you are the idea of an altered microbiome, or the bacteria that live within us and are important for immune health, the idea that this may have changed due to some environmental factor, and also an altered diet, and the idea that the timing of the exposure to a food may influence whether the body becomes allergic or tolerant to that food. So first, let's talk about food allergy in the microbiome, or more broadly, what is referred to as the hygiene hypothesis. So although we don't understand why food allergy is rising, this is the most well-accepted explanation for the epidemic. And so the hygiene hypothesis originally suggested that infection promoted a healthy immune system, but over the years this has been modified to recognize that mutualistic and commensal microbial exposures, like those that live in the intestinal tract, are important for the development of immune function. So with respect to food allergy, there are several exposures that affect the microbiome, including mode of delivery, birth order, family size, exposure to daycare, farming lifestyle, exposure to animals, exposure to certain bacteria, and then environmental antimicrobial chemical exposure, which is my particular area of interest. And all of these have been shown to be associated with an increased risk of food allergy. And so the underlying hypothesis here with respect to food allergy is that there is a specific environmental exposure that influences the microbiome and changes the immune system towards an allergic phenotype to food allergy. So the reason that I got interested in the microbiome and food allergy is because of a paper that we published looking at the relationship between exposures to environmental antimicrobial chemicals and allergen sensitization, or having a positive test to a food allergy. So we studied a nationally representative group of over 800 children, and we found that children with the highest levels of triclosan in their urine were almost twice as likely to have food sensitization or test positive for allergy. For food allergy. And so at this point, this is a correlation. Right now, we cannot conclude that this chemical is causing food allergy, but this is something that we're working on. And I'll tell you more about triclosan in a moment. We also looked at aeroallergen sensitization, or testing positive for allergy to particles in the air like dust mites or pollens. And we found that the likelihood of aeroallergen sensitization increased with increasing triclosan levels. We also found that propyl and butylparaben, which are two other antimicrobial chemicals, were also positively associated with aeroallergen sensitization. And again, this is a correlation. We're not yet able to say if this is the cause of allergic sensitization. So because I'm an allergist, I was also interested in triclosan and asthma, and we showed that among current asthmatics, higher triclosan levels are related to having a 70% greater likelihood of reporting an asthma attack in the last year. And so we found this really interesting because triclosan may not just be causing disease, but it may actually affect the control of the disease here with asthma. So I've talked a lot about triclosan and a bit about parabens as well. So let's talk now about their sources. So of course, there are hand sanitizers, and these can be generally alcohol-based, but they may also contain triclosan, which was invented about 40 years ago, and it's been incorporated into many personal care products, primarily because of its antimicrobial effects. Parabens are used as preservatives, and they're found in many body lotions, hair products, and cosmetics. And this is actually a real-life photo of all the products in my house that contain triclosan and parabens. So I suspect that you guys all have similar products in your home as well. So I focused on triclosan and parabens because these can be actually measured in body fluids, but it's important to mention that there are many antimicrobial chemicals that we are potentially exposed to, as triclosan and parabens and other antimicrobials are being incorporated into durable goods, including clothing and instruments that we use in the hospital, and things that we and our children use every day. So even if we try to avoid exposure by not using these products, they have entered the water supply and are now found in agricultural produce, so it's very hard to avoid them. So our group is actively looking at whether these particular chemical exposures may in part underlie the recent rise in food allergy that we have seen. So now I'm going to switch gears and talk about another idea that's gotten a lot of attention lately related to food allergy. And this is the idea that the timing of allergen exposure, or when the immune system first sees a particular allergen or food, influences whether or not an individual becomes allergic to that food. So in the year 2000, the American Academy of Pediatrics recommended that children who have a risk of food allergy avoid peanut until the age of 3. And this was really in response to the perception that food allergy was rising and we need to do something about it. And the idea that was accepted at the time was that you cannot become allergic to a food unless you are exposed to it. So unfortunately, over the next few years, the rate of food allergy in the US continued to increase, still at an alarming rate, and people began to question whether food ingestion rather than avoidance may be the best way to prevent allergy. So one group that really pushed this issue recognized that children from the same genetic background have very different rates of peanut allergy when they live in different environments. And so this group compared the rate of peanut allergy in Israeli children to that of Jewish children living in England. So the two groups were generally thought to be similar, of a similar genetic background. And they found that peanut allergy in the Israeli children was very rare, while in England it was similar to the rates seen in the United States. And they looked for different explanations, and what they found that was most likely to explain this difference was that in Israel, it's very common to feed infants a soft snack made with peanut flour, very similar to how we feed babies in the United States, these wheat biscuits. However, in England, where mothers were really following the guidelines and not introducing peanut until after age 3, peanut allergy was 10 times higher. And this data was very suggestive that delaying introduction of peanut was actually causing peanut allergy. But because this data was observational, it was really not able to prove that early exposure could prevent peanut allergy. So now we actually do have evidence from a very convincing study done by the same group to support the idea that early allergen exposure can prevent the development of allergy. And here the example is still for peanut. So this is data from a randomized trial of over 600 infants who were aged 4 to 11 months, and they were identified as being high risk for peanut allergy on the basis of already having developed eczema or egg allergy. And these children were randomized to either consume or avoid peanut until the age of 5. And at that time, they were assessed for peanut allergy. So it's not hard to see from this figure that the group who avoided peanut had a roughly 5-fold increase in the risk of peanut allergy compared to those in the consumption group. So this study just came out earlier this year, and it's definitely going to change our management of food allergy. And hopefully because of this, we will see a decline in peanut allergy and food allergy in general. So, but what about the people who already have food allergy? So as Dr. Schreffler mentioned, our current treatments, as you know, are very limited. We tell patients to strictly avoid the food that they are allergic to. This is difficult to accomplish. This can severely impact quality of life, and it may impose nutritional risks. We also wait for the allergies to be outgrown, but peanut and other allergies are usually lifelong, and I've showed you evidence that other allergies such as egg are more persistent. So we also treat allergic reactions when they occur, but reactions can be severe and unfortunately sometimes even fatal. So moving forward, I would urge you to think about the search for a cure for food allergy on a spectrum of prevention. Primary prevention refers to preventing the development of risk factors for disease, or in the food allergy example, this can refer to preventing healthy people from developing food sensitization. And in the future, we may show that food sensitization can be prevented by avoiding specific antimicrobial chemical exposures or manipulating the microbiome in other ways. Secondary prevention refers to preventing the development of disease in those with risk factors, or using the food allergy an example, preventing those who are sensitized from developing food allergy. And from the peanut consumption study, it looks like early allergen exposure may really help here. And finally, tertiary prevention refers to inducing remission of disease in those with food allergy. And there are current trials of allergen immunotherapy protocols that were discussed earlier that are very promising in protecting individuals from having severe allergic reactions, but they're not quite ready for prime time. So what is needed to get to the point where we can truly cure food allergy? So there are many questions that need answering, and I've just listed a few here that are needed, which is really knowing exactly what the causes of food allergy are, knowing how to identify the children at high risk of food allergy so that we can target them with early allergen exposure, and then knowing what features of the microbiome are important for immune development, and especially as it relates to food allergy. And finally, we do need people to volunteer for research studies so that we can learn from them, and we need agencies to support our research so that we can find these important answers. And I want to thank you for your time, and please feel free to get in touch, and thanks a lot for attending.
Thank you, Dr. Savage. Next, I have the pleasure of inviting Dr. Xavier. Ron Xavier is an institute member of the Broad of MIT and Harvard. He's also chief of gastroenterology at Mass General and the Kurt Isselbacher Professor of Medicine at Harvard Medical School. He directs Mass General's Center for the Study of Inflammatory Bowel Disease as well. As a clinical gastroenterologist and molecular biologist, he studies the specific mechanisms involved in innate and adaptive immunity, as well as the genetic variants associated with Crohn's disease, ulcerative colitis, and autoimmunity. His laboratory uses genetic, structural, computational, animal models, and clinical research to define the mechanisms controlling inflammation and immunity in vivo. Recent studies have focused on understanding how the gut microbiome contributes to allergy and autoimmunity. I have the pleasure of collaborating with Dr. Xavier on one of the Allergy and Asthma Disease Center grants. I can tell you he's both an excellent scientist and excellent speaker, and let's please welcome him.
Thank you. What I'll try to do in the next 15 minutes is give you sort of an understanding of what happens in our gut. So what I'm showing you here is the layers of the gut. So if you look at our oral cavity all the way to the colon and look at the cells that line the gut, the lining of the gut is lined by what we call these epithelial cells. So these are cells that line, for example, the skin. They are similar in appearance in the gut, and they play an important role in absorbing food. So they are essential for nutrient absorption. We also know that in the gut there are a load of bacteria, viruses, and fungi. While sort of having to absorb food, it also has an important role in defense, so keeping these bacteria away from getting into the system. So to prevent that, there is a large number of immune cells. You heard about some of these immune cells in Wayne's initial introduction. There are these cells that have processes called dendritic cells. There are T cells and B cells. So in our gut at all times, there is activity of all these cells that work to control inflammation so that the gut can absorb food, maintain a barrier, and provide an immune system. And all of these factors have to function for us to grow, for us to think, and for us to avoid disease. There are lots of things that affect our gut function. So obviously the food we eat, the genes that we have. So you heard about some of the genetic diseases in the previous two talks. Obviously stress and the load of antibiotics that one might take. So there are many factors. Surprisingly, all of these factors induce the same reaction. So what I'm going to tell you are a couple of stories. The first is a story, and before I get to those stories, I'll tell you a little bit about the gut bugs. So within us, there is a huge load of bacteria. So for every human cell in the body, there are about 10 bacterial cells. So we have about 20,000 genes. The bacteria in us account for about 8 million genes. So you can just imagine how much damage these bacteria can cause. The other is that there are about 10,000 different species of these bacteria. So I keep adding numbers. But I think the most striking thing is that 2 to 6 pounds of our body weight is accounted by the gut bacteria. So there's a huge load of these bugs, and that's why I spent a few minutes talking about the immune system that has to keep these bugs away from getting into the system. Having said that, these bugs are important. Having normal bugs in the gut prevent bugs like Salmonella, the infectious organisms, from getting in. They also digest our complex polysaccharides, the complex carbohydrates. They help synthesize vitamins, and they're important for the immune system. So the couple of stories that I'm going to tell you is, are we having this increase in spike of allergic diseases because we are losing our friends? Or is it because of the food we eat? So the first example was a study where investigators looked at the diet in Europe. So this was done in Florence, Italy, where the food looked very much like the food we eat, a Western diet that was high in animal protein, sugar, starch, and fat, and low in fiber. They compared the diet in a group of kids who lived in Burkina Faso in Africa, where they ate a high fiber diet, rich in starch, fiber, and plant polysaccharides, but low in fat and animal protein. So just the diet and where these kids were born. Now, if you look at the bacteria, so that 10,000 species in the gut, were they different in these two communities? And you can see how striking it is. So the kids born in Burkina Faso had this large green blotch of bacteria that was mostly absent in the kids born in Florence. And these bacteria are these bacteria called Prevalence species that play an important role in secreting certain good stuff that keeps these bugs from getting in. So if you look at these kids and ask the question, what types of short-chain fatty acids, so these are these products that these bacteria make. If you look at the kids born in Burkina Faso, shown in black, versus the kids born in Italy, shown in light gray here, you can see that the kids who ate a high fiber diet, low in meat products and low in fat, made a lot more of these short-chain fatty acids. Making short-chain fatty acids is good for you because not only does it keep the gut health good, these kids were also protected from a number of infectious diseases such as Salmonella, Shigella, and various infections. So the first example is how diet plays an important role in educating the immune system, and how diet and its good effects can play an important role in preventing certain infections. The second example that I'm going to tell you is that if you look at the consumption of wheat across the world, if you look at that picture over here and look at the burden of a disease called celiac disease, it more or less has a mirror image. So you eat more wheat, you have a high incidence of celiac disease in those countries. So what is celiac disease? It's a reaction to a protein called gluten, which is the major wheat storage protein. And within it, there are certain fractions that have an important role in introducing or inducing immunity. So usually celiac disease presents in kids at the time of weaning, so it makes sense as you're introduced into these products. There is another spike so these kids often can improve during adolescence, but then this disease can obviously present at any time as you grow. So what are the symptoms in these kids and adults? So you can see that kids can present with very vague symptoms, lack of energy, but the most striking symptoms are diarrhea, weight loss, and abdominal distension. And if you look at adults when they get celiac disease, the dominant symptoms are more sort of lack of energy, diarrhea, and so forth. So the gut is a funny organ. It reacts to stress in a very ordered fashion. You get abdominal pain, you get diarrhea, you get bloating, and some of the symptoms that I've listed here. Obviously, celiac disease causes a defective absorption of other products, other foodstuffs. So you then, with long-standing celiac disease, you can affect your various other metabolic processes, and these patients can have bone pain. So why do people get celiac disease? One, because they have a number of abnormal genes that predispose you to celiac disease. Obviously, you have to see a diet that's rich in gluten-containing wheat products. And there is now evidence that, so why would a kid who's 12 years old, who has the genetics of celiac disease, who's been eating wheat all along, gets celiac disease at the age of 12. The current thinking is that these children are at high risk for celiac disease, but now got an infection from a virus that tipped the balance. So it's not uncommon where you see patients coming into your clinic and saying, I've been fine tolerating wheat for 20, 30, 40, 50 years, but then I got this viral infection, and since then I'm having diarrhea. And it's not uncommon to find these patients have a new diagnosis of celiac disease. So if you again go into the gut of these patients, the lining is completely flat, so you don't see these nice processes that you see there. And as a result of this, you're unable to absorb several of the food stuff that you take in orally. If you stop eating gluten, then you have a real opportunity to get back to the normal state. So a little bit of immunology following up on what Wayne outlined. So in the normal setting, you have a lining that has lined by this very ordered set of epithelial cells. And in celiac disease, you make certain T cells that start attacking the epithelial cells because they react to that gluten-containing peptide. So that now you end up with these flattened, abnormal-shaped epithelial cells that not only cannot absorb food, but also sets you up for an increasing antigen load. So once you damage this epithelium, you can see that these gluten peptides can get through and start triggering these T cells. So you get persistent inflammation and damage of this lining. So how do you make a diagnosis of celiac disease? Obviously, you can check for antibodies against celiac disease. Obviously, you have to ask the patient whether he or she is taking gluten, and if he or she denies that they take gluten, then obviously it's another cause for the allergic disease of the gut. And then obviously you'll also have to take a history of whether there are other food intolerances in these patients. And if you have a serology test or a blood test that is positive for celiac, then most likely that you have the disease. Very rarely you have to do an endoscopy and biopsy to make the diagnosis. How do you treat celiac disease? You stop eating gluten. Obviously, we'd like to live in a world where you can eat gluten. So there are a number of companies that are trying to find ways of allowing people to enjoy bread, but then hopefully find a vaccination strategy that might allow them to overcome these reaction to the gluten peptides. So that's story number 2. Number 3 is that we eat lots of different foods. So from meats to fish to bread to fruits. That gets into our GI system. So this is the oral cavity, gets into the esophagus, this pipe here, and that gets into the stomach where it's digested by mostly acid and containing enzymes. Comes down into the small bowel. Now we are getting into bacteria territory. These nutrients get absorbed through these lining and get across the epithelial barrier so that you can absorb essential nutrients, carbohydrates, proteins, and so forth. The bacteria stay active, so in response to the bacteria, this epithelial lining makes antibiotic-like molecules that keeps these bacteria at bay. What can go wrong? So I'm going to talk to you about a condition called eosinophilic esophagitis. This is a diagnosis that we are making more often. It can affect children all the way to adults, and it's thought to be sort of an allergic reaction to food. We don't know the cause. So in the case of celiac disease, we know that it's gluten. In the case of eosinophilic esophagitis, we are yet to identify what's the trigger. So these patients often present with difficulty swallowing. It's not uncommon for a 60-year-old patient to show up in the clinic and say, I was able to eat my food okay, but all of a sudden my food got stuck in the esophagus. And they can have nausea, vomiting, and abdominal pain. Obviously you do a blood test and their celiac antibody test comes back negative, so you know that this patient is unlikely to have celiac disease. but clearly has symptoms of dysphagia, so difficulty swallowing. And when you put a endoscopy down here, the throat, you can find that the esophagus has a ring-like structure. And if you were to biopsy that esophagus and look under the microscope, you see these cells called eosinophils. They are very nice cells. Normally, you see very few of these cells in the esophagus. But in this condition called eosinophilic esophagitis, you see many more cells. Obviously, we are now several groups are working towards identifying molecular tests to diagnose this, so to see whether you can avoid having to put a scope down and take a biopsy. And the hope is that with time, there would be different types of molecular diagnostics that would allow us to make a diagnosis of eosinophilic esophagitis. And finally, I'll end by sort of repeating what the two previous speakers have said. So obviously, the burden of food allergies affects about 4 to 10% of kids. The good news is that almost majority of these kids outgrow their allergy if they are exposed to these foods early in life, as Dr. Savage said. Obviously, there are persistent allergies that can cause trouble, and Wayne and Dr. Savage both outlined how one might make a diagnosis and treat it. Obviously, in a history from a patient, you have to take into note several factors. So the timing of exposure, the route of exposure, the nature of reaction, and the duration of symptoms. But clearly, the symptoms can affect any part of the organ system. So you can have eyes affected, so that's an ocular allergy. You can have skin affected, that looks more like dermatitis. But then you can have, wheezing to dysphagia to diarrhea and abdominal pain. So the challenge with allergic diseases of the GI tract is that its symptom complex can affect any part of the GI tract. So where are we going in the future? The hope is that we'll be able to generate these allergen chips that will have the allergic determinants of all these foodstuffs that would be spotted on this chip. And just like doing an expression array, one might be able to take blood from these individuals who are at risk and measure the reaction to these allergic tests. So rather than getting those needles under your skin, maybe there is the opportunity to sort of create these allergen chips that might be able to sort of tell you what am I allergic to. Obviously, the diagnosis is you have to take a good history, skin test for the time being, try to identify the disease-causing allergens, and then try to manage the diagnosis or the allergy. So I think I'll stop there, but what I've tried to tell you in the last 15 minutes, that there is clearly an increasing number of patients who are presenting with food-derived allergies, and this is from children to adults. Clearly, the immune system is important, and as Jessica mentioned, the gut bugs might also be important. Normally, we live at peace, in harmony. The food we eat gets absorbed by the gut. The immune system has a nice way of ignoring the food antigens, and the gut bugs behave. And that condition is referred to as tolerance. When tolerance breaks down, you end up with diseases such as allergy, asthma, and maybe some autoimmune disease. I think I'll stop there. Thank you.
Thank you, Dr. Xavier. So we're now going to ask you two to have a seat over there, and I get to distribute the questions from the audience that we've collected and put you guys on the hot seat a little bit, and I'll try to take a few of them myself. Maybe I'll start with this one for Ramnik. The question, you've talked about the role of the microbiome in health and its potential as a modulator of food allergies. Can probiotics help?
So a properly designed probiotic is likely to help. The challenge with the current probiotics is they were designed without paying a lot of attention to the microbiome and what microbiome changes in the gut in states of allergy. So when Dr. Savage finishes her studies, we'll be able to identify, what bacteria have changed in patients with and without allergic disease. And then you would design the probiotic that would try to correct the missing bacteria in the gut. So clearly in the future, there is a role for this. But right now, most of these are designed in such a way that they are a general probiotic that's thought to help every disease, and that often is not the case.
So there is very preliminary, probably poor evidence that probiotics can help prevent eczema, but these are very small, poorly designed studies, and there's no study specifically for food allergy. So I just wanted to add that in, but generally we're not saying that these are a great thing, but hopefully in the future they will be.
Probiotics are also being evaluated for their potential to essentially improve oral immunotherapy outcomes. And some of you may, because it got pretty broad press coverage, have seen a study that came from investigators in Australia where they combined the use of LGG, a commonly used probiotic, with oral immunotherapy. And it was widely reported as the outcomes in that OIT-treated group being perhaps better. But one of the, serious weaknesses of the study, which the authors acknowledged, but kind of got lost in the press coverage of it, is that there was not a direct comparison arm of OIT without probiotic, and the comparison was actually to oral immunotherapy outcomes in other studies, which is, a very significant limitation. I have a question for Dr. Savage here. Is it true that allergies can have their onset later in life? And I guess we could restrict that to food allergies.
Yeah, so definitely food allergy can have an onset later in life, and generally these are restricted to certain characteristic foods, such as nuts and fish. And there are also some patterns that we see related to environmental allergies. So it's really unusual to have a new onset, say milk or egg allergy, present after the age of, after early childhood.
Yeah, I agree with that. I'll take one question. The question from the audience was, can people become sensitized by allergy testing? And I think that this is maybe an important one to address because it's kind of clinically relevant. And I've told you that you need sort of a primary exposure to the allergen to then become sensitized and allergic, and so it's a very sensible question. It turns out that these allergens are actually quite prevalent in the environment, and early exposure seems to occur very early on, perhaps primarily through the skin. Certainly there's gut exposure as well. You can measure food allergens in public dust samples, so it's very prevalent. There does not appear to be any increased risk of allergy as a result of allergy testing. Anything you want to add to that?
No, I agree.
So a question for Ramnik. This person is wondering if the changes to the mucosa of the GI tract occur when they occur relative to gluten exposure. Is that a precondition that celiac individuals have, or is that something that's induced by the exposure to the antigen?
So the damage to the lining is in fact induced by the antigen. There are the pictures that I showed you are in patients who had the gluten antigen exposure and had an immune reaction to it. Now there is early evidence, if you look at individuals who are genetically predisposed or at genetic risk for celiac disease, with ultra special tests, one might be able to see subtle changes in the epithelial lining of the gut that might tell you that these individuals are at slightly higher risk compared to those who don't have the genetic mutations. But under a microscope, they are hard to find, but if you do molecular DNA tests, you might be able to find these differences.
And maybe a follow-up to that. So some people may be aware that in relatives of people with celiac disease, there might be some evidence of immune abnormalities. Could you comment on that?
Yeah, so it's the same. So first-degree relatives, if you look at first-degree relatives of celiac disease, and you do some of the ultra-sensitive immunological tests, they also have some of these tests that look like they are celiac-like. Now, there is another broad condition called non-gluten sensitive disease, or non-gluten NGS disease. And these are individuals who don't have celiac disease but who are sensitive to the gluten peptide and have some of the features, the clinical features of celiac disease. But I think I would recommend that you make a very careful diagnosis of the right disease before you go off gluten, because living on a gluten-free diet is about 3 times as expensive than enjoying regular food.
Excellent. This is a question for Dr. Savage. The question was, what makes a child, quote unquote, high risk to an allergen if they haven't been exposed to it? And I think that this is a particularly relevant question in light of the LEAP study that you showed us that just came out a few weeks ago and that got a lot of press coverage. I know that we're fielding a lot of questions about whether, parents are questions from parents of very young children about whether they should introduce peanut. Are they in this high-risk category? Maybe you can comment on how the authors defined it, and then how we think about it in general, and how we might generalize the findings of that study to a broader population. That's a tough one, I realize.
So in that study, they chose children that they thought were likely to develop peanut allergy. And they did this because they wanted to sort of enrich their study group for people who are likely to have the outcomes. They didn't have to pay all the money to have a really, really large study. So they picked children with eczema already, and they had to have pretty severe eczema. And they also picked people who tested positive for egg allergy, to have relatively high levels of egg allergy testing, like a large skin prick test size, so that we were pretty confident that they did in fact have egg allergy. So you had to meet one of those 2 criteria to get into that study. And so these are people who are considered to be high risk because they've already declared themselves to have an allergic phenotype by virtue of them having eczema, which we consider one of the allergic diseases. And we know from other studies that kids who develop eczema are likely to go on to develop food allergy. And they also considered them to be high risk to develop peanut allergy because they had evidence of egg allergy. So we know that having one food allergy makes you more likely to have another food allergy because they tend to go together. So that was sort of how they defined it in the study. We define it kind of depends on who we're talking to, how we define it. But a child, if you're seeing a patient in clinic talking about whether or not they might be high risk, you might consider if they have a sibling who has food allergy, if the child already has declared themselves to have eczema, or if their parents have allergies or not. And so those are some of the things that we consider. Usually you're talking about an infant who probably hasn't developed other allergic diseases like asthma or hay fever at that time. And I think, we're all sort of grappling with how are we going to sort of deal with incorporating this, the results of this study into our practice. I think my thoughts are sort of to expand our definition of high risk sort of beyond what they did in the study and use the broader definition of people with a family history or people who have any reason to think that they might be on the path to developing food allergy and consider getting these allergenic foods into their diet earlier. I don't know if you want to add to that.
Yeah, I mean, well, it's a tricky question. I mean, I sometimes joke because we sort of saw, the Leap handwriting on the wall, as it were. In other words, you may be familiar that, in 2000 it used to be avoid, avoid, avoid. Dr. Savage, kind of touched on this, and then the guidelines essentially became kind of agnostic. Like, we're not sure if you should eat or not, but just eat what you want. And now we have this kind of interventional study that points in the direction that early exposure, at least for IgE-mediated allergy, is beneficial, at least for peanut. But it is a very high-risk cohort, and I sometimes worry that this will now be the latest and greatest way that we make people neurotic, is that, oh my goodness, did I give, Sally her peanut today? And it's really important to recognize that, as Dr. Savage said, that was an extremely enriched population for peanut allergy, and in fact, even in the intervention group. So even though that effect of prevention was enormous, from almost 20% to 3%, 3% is still well above the general population prevalence for peanut allergy at 5 years of age. So this was a truly very strongly allergy skewed group, and I think in terms of what most parents should do for most kids, it's probably not going to make a lot of difference one way or the other, whether or not they introduce peanut early. Most of them are not going to become peanut allergic. And yet, it is a very real issue, and obviously people want very clear guidance. And I think, like Dr. Savage, we'll test more broadly probably than we did, and we'll try to figure out how to get it in earlier than we did before. But it's by no means very straightforward, and for most people, I think it's not going to matter. Which is the good news. There's a question here, Ramnik, on lactose intolerance. So the question is, kind of how that fits in the scheme, and is it age-related? Maybe you could comment on that, and maybe, across the populations.
So there's clearly a population distribution of lactose intolerance. Often the diagnosis is made early in life. But again, this same idea of the viral hypothesis, where you get a viral infection late in life or a gastrointestinal infection late in life, and then you fail to tolerate milk products after that infection, so triggering sort of I don't want to use the word acquired, but sort of a state where you now make less of that enzyme to digest the milk products. And so they basically have a clinical presentation that looks a lot like lactose intolerance. The late onset lactose intolerance can be transient, so it can last for a short time and then you can recover. But in a subset of patients, they can be lactose intolerant for a long time. Mm-hmm. So it's thought to be a second trigger, or the second hit hypothesis, that triggers the late onset diagnosis of lactose intolerance.
There are a couple questions here on kind of the nature of allergens. One of them asks, why peanuts of all foods? What makes them special? The other asks about adverse reactions to papain. And this is, I think, a question that the field has pondered for a long time. If you look at sort of the proteome of things that we're exposed to, so the wide diversity of proteins that the human immune system encounters, it is a very small subset, in fact about 0.8% of all structural protein families that account for the large majority, well over 80%, of all described food allergens. And it's also, even now if we add in respiratory allergen, and papain, by the way, is probably more of an occupational allergen than it is a common food allergen, although it can be the case. It really points to a few things, stability to digestion, things like that, but also probably ways in which these particular protein structures can stimulate, or things that they kind of come along with can stimulate the immune response. Dr. Xavier mentioned in one of his closing slides this concept of component-resolved allergy diagnostics, and that's actually something that's available here and now, and helpful in narrowly defined cases. And it just recognizes the fact that, peanut or wheat or milk is not one thing. There are actually multiple distinct proteins there, some of which are recognized by the immune system as allergens, and others that are not, some of which are more associated with potentially severe reactions than others. Some of them highly cross-reactive with environmental allergens and not associated with severe allergy. So that evolution in diagnostic testing in a couple of cases is already available and something that is genuinely useful. There's one quick question to Dr. Savage. Should we be avoiding hand sanitizers?
Then I
It's
won't
not
have
just for
anything
Dr.
to study.
Savage, since it's blood.
So, we don't know. So hand sanitizers are mostly alcohol-based, and we don't think that the alcohol is absorbed systemically. We think it probably changes the types of bacteria that are on your hands. It probably kills them. But by the time you are using hand sanitizers, it's probably too late to make any difference if these things are causing anything anyway. The reason we use hand sanitizers, at least in the hospital, is to prevent very sick patients from getting sicker. There are really good reasons to use them in certain situations. So I think you just use things as you need them and limit things that you don't need.
Great. Yeah, I agree. And the Joint Commission will agree that we should be using our hand sanitizers in and out of seeing patients. So another one for you, Jessica. Asian cuisine has lots of peanuts. Any study on peanut allergy for the Asian population? And maybe bundled with that, just a reminder, I know you touched on this, but there are a few questions on, sort of that sort of geographic pattern, maybe specifically on peanut allergy.
Right. So I am not recalling the data exactly perfectly, but I believe that nut allergy is not quite as common in Asia as it is in the United States. And so the countries where we're seeing huge rises or a very high prevalence of food allergy are, North America, Western Europe, and Australia. And so these countries all, we think, generally have similar lifestyle, similar foods, and something about them that is similar, which we have not yet identified as contributing to this high rate of food allergy.
Great. This might be the last question. So let me see if I can spice it up a little bit. So the question was, not that the question needs to be spiced up. Question was, why now do people in America eat a more gluten-free diet? And I guess kind of the, well, let me just pass that on to you, Ramnik. So I guess in part, is this a fad? What do we think is really going on? Is there more celiac disease? What do you make of the non-celiac gluten intolerance? I know you urged us that we need to get a good diagnosis before we avoid, and I firmly agree, but do you think that there's anything there, and if so, do you think it's immune-mediated?
So I think there was a recent New York article on sort of the gluten-free diet industry, how it's moved, exploded in the United States. So I think clearly in celiac patients, avoiding gluten is essential. There is a large group of diseases that are bundled in this non-gluten sensitive or non-gluten syndromes where they have clinical symptoms that correlate with the intake of gluten, but very little tests that you can do to show that there is a reaction to gluten. I think so if you, just for numbers, so if you say 10% of patients have a diagnosis of non-gluten sensitive enteropathy, it's only in about 0.1% does being on a gluten-free diet does their symptoms get better. The rest, end up going on a gluten-free diet, spending a lot more money without, clear evidence that their GI symptoms have improved. But once they're hooked on that diet, they rarely get off it, and they're willing to spend the extra money to stay on it.
Well, I can tell you it's certainly helpful for my patients who have other forms of wheat allergy. So people can obviously have IgE-mediated allergy to wheat, and so the proliferation of those products is helpful for them as well. But I think that we will have to leave it there. We're out of time. I thank the audience for your engagement and participation, and I want to thank our speakers again for their presentations.